Hello and welcome to the final episode of my mini-series about sequences and recurrence relations. I will still make videos on this topic occasionally, but at least in the near future I will be covering different topics. Still, I have this crazy problem right here, which will be quite interesting. It says that sequence AN is given as A1 equals 1 and A2 equals 0, and this Sn is the partial sum. Then we have an plus 1 equals Sn squared over Sn minus 1 plus n minus 1 times Sn for all natural numbers n greater than or equal to 2. So obviously, first we have to simplify this recurrence relation. And in order to do that, we have to use this relation between an and Sn. The best way to apply this method is to change this an plus 1 into Sn plus 1 minus Sn. Then the recurrence relation becomes Sn plus 1 minus Sn equals Sn squared over Sn minus 1, then plus n times Sn minus Sn. So cancelling Sn plus 1 equals Sn squared over Sn minus 1 plus n times Sn. So now only partial sums are involved in the recurrence relation. To handle this recurrence relation, we divide both sides with Sn. Sn plus 1 over Sn equals Sn over Sn minus 1 plus n. Actually, in order to divide with Sn in the first place, it must be guaranteed that Sn does not become 0 for all natural numbers n greater than or equal to 2, but I will not discuss that in detail here, because it is pretty obvious that Sn is positive from how this sequence is defined in the first place. So back to here. Let us use substitution and let Bn be Sn plus 1 divided by Sn. Then we can write the recurrence relation as Bn equals Bn minus 1 plus n for all natural numbers n greater than or equal to 2. This is the typical easy recurrence relation given as the difference Bn minus 1, which is easily solvable. Here let us find B1 first, which is S2 divided by S1. And S2 is given as A1 plus A2, and S1 is just A1. So it is 1 plus 0 divided by 1, which is 1. Now, in order to find the general term Bn, we have to add up differences b sub k minus b sub k minus 1 up to k equals n. And here, this difference is given as k. So we have Bn equals B1, which is 1, plus sigma k from k equals 2 to k equals n. So we have 1 plus 2 plus 3 plus 4 plus so on plus n, which is the sum of consecutive natural numbers, which is given by the simple formula n plus 1 over 2. Notice that even though we have calculated B1 equals 1 separately, you can see that the result also holds for n equals 1, so we can say that Bn is given as n plus 1 divided by 2 for all natural numbers n. So we have Sn plus 1 divided by Sn given as n plus 1 divided by 2 for all natural numbers n. The next step is to solve this recurrence relation and obtain the expression for Sn. Here, instead of differences, now we are given ratios between adjacent terms, which is also the basic type. Here, Sn can be obtained by the first term S1, then multiplying the ratios S2 over S1, S3 over S2, S4 over S3, and so on, up to Sn over Sn minus 1, which can be obtained from here. Or we can write S1 times the product notation pi, then sk plus 1 over sk from k equals 1 to n minus 1. Here, S1 is just A1, which is 1, so we have Sn equals 1 times product pi k plus 1 over 2 which is 1 times 2 over 2 times 2 times 3 over 2 times 3 times 4 over 2, and so on. And for the case where k equals n minus 1, we have n minus 1 times n over 2. Here, in the numerator, we have 1 squared, then times 2 squared, then 3 squared, and so on, up to n minus 1 squared. Then we have this n. And in the denominator, we have bunch of 2's, or more specifically, n minus 1 2's. So we have 2 to the power of n minus 1 in the denominator. And we can write this as n at the front, then 1 times 2 times 3 times n minus 1 squared divided by 2 to the power of n minus 1, which is n times n minus 1 factorial squared divided by 2 to the power of n minus 1. And this result also works for n equals 1, so we can say Sn is given like this for all natural numbers n. So we have solved for Sn, the partial sum, and we have reached the final stage. Now we can finally solve for An, again using the relation between an nth term and a partial sum. But we have to be careful here, since this relation only holds for n greater than or equal to 2, which means that a1 should be defined separately. So a1 equals 1, as given in the problem. And when n is greater than or equal to 2, an equals Sn minus Sn minus 1. So from here, we have n minus 1 factorial squared over 2 to the power of n minus 1 minus, now we have n minus 1 times n minus 2 factorial squared divided by 2 to the power of n minus 2. Here, in order to make common parts, in the first term, let us write n, then n minus 2 factorial squared, then we will need n minus 1 squared at the outside. So we have this over 2 to the power of n minus 1, and in the second term, we write the same numerator. But in the denominator, let us write 2 to the power of n minus 1 instead of 2 to the power of n minus 2. This means that we have to write additional 2 in the numerator. Then we have the common part, which is this part. So let's write n minus 2 factorial squared over 2 to the power of n minus 1 at the front. So this times, in the first term, we have n minus 1 squared left. And in the second term, we have minus 2 n minus 1 left. So we have this, and we have n minus 1 common. So we can write n minus 1 here. Then we have n minus 1 minus 2. So we have this times n squared minus n minus 2. And this part is actually factorable. So we have this times n plus 1 times n minus 2. Notice that this expression gives a2 equals 0 as given in the problem. So we can say that this result is true for all natural numbers n greater than or equal to 2. So the final answer is a1 is given as 1. And when n is greater than or equal to 2, an is given as, first, 1 over 2 to the power of n minus 1 in the polynomial part. So n plus 1 times n minus 1 times n minus 2. Then the factorial part, n minus 2 factorial squared. So we have obtained this beautiful answer. We have utilized the combined knowledge about sequences and recurrence relations we have learned so far and managed to solve much more difficult one. And if you're interested in this topic but haven't seen my previous video of this series, please go check this video where I solved another recurrence relation. And as always, I will see you in another video.